All right. In this video, we're going to go over or begin going over chapter 17 and learning about chemical equilibria. If you remember from the previous chapter 16, the rate of a reaction is equal to some rate constant K times its components, its reactants, to some reaction orders, M and N. Okay. Now, normally M and N are different than the coefficients, but there are situations where M and N can match the coefficients. Now, we're going to take this and we're going to apply it to this idea of equilibrium, right? So note we have a rate here, and rate we write rate laws based on the concentrations of the reactant and the rate constant in the forward direction, right? However, at equilibrium, the forward rate and the reverse rate are equal, meaning as quickly as we form C and D, we reform A and B, right? So the concentrations will appear to be constant at equilibrium, when in reality, it's in this cycle of forming reactants forming products and products forming reactants. And until we do something to the system, it will just keep doing that, but visually it'll appear to have stopped. So the way that we can express this using this equation is as a ratio of rate laws. So first, let's assume that coefficient M is equal to A and N is equal to B. In other words, let's assume that our reaction orders for each reactant are their coefficients, right? So that would mean then that the forward rate law is going to be equal to the forward rate constant times the concentration of A to the power of A and the concentration of B to the power of B. We can also have the reverse rate, which is equal to K reverse. And when going in reverse, the reactants are the products. So C to the C and D to the D. Okay. Now remember, at equilibrium, the forward rate equals the reverse rate. So that means we can take these two rate laws and set them equal to one another. Okay, so there we have the forward rate law, and here we have the reverse rate law. We can then further take that and rearrange it such that the rate constants are on one side and the concentrations are on the other. So we'll divide both sides by A to the A and B to the B, and we'll divide both sides by K reverse. And so we end up with the following expression. And so we can see here the ratio of rate constants. Note a constant divided by a constant would give us a constant. And that gives us something known as capital K C, which is the equilibrium constant. Okay, so the equilibrium constant is the ratio of rate constants, right? But can also be described as the ratio of concentrations of products over reactants. And this is at constant temperature. That's important. If you remember from the previous chapter, the Arrhenius equation shows that temperature affects rate constants, and thus an equilibrium constant is only true at a particular temperature for a particular reaction. If we change the temperature, it will change the ratio of rate constants when it will change what the ratio of rate constants is at equilibrium. And later in this chapter, you're going to learn that dependent upon certain parameters of the reaction, an increase in temperature could increase the rate constant, or it could decrease the not rate constant. An increase in temperature could increase the equilibrium constant, or it could decrease the equilibrium constant, dependent upon some parameters of the reaction itself, okay, which we'll visit later. So this is called an equilibrium expression. Okay, this is called an equilibrium expression. I'm going to be using it a lot over the next 3 chapters. Okay, and we can write it for any reaction that reaches equilibrium. Now, some things to note here, some terminologies. When K is approximately 1, well, let's do it this way. When K is much greater than 1, we call that type of equilibrium product favored. What that means is at equilibrium, the concentration of products is significantly greater than the concentration of reactants. So in other words, at the point where the forward and the reverse rates are equal, there will be a higher concentration of products, more particles per volume of products than reactants, okay? We could also have the flip side of that, where K is less than 1, and that is a reactant favored scenario. And so then at equilibrium, now and so again, remember what it is at equilibrium. The rates are equal, right? The forward and reverse rates are equal. A reactant favored reaction, okay, and thus the equilibrium constant is less than 1. I will say Kc since they're dealing with concentrations. The concentration of the products will generally be lower than the concentration of reactants, okay? And then, of course, we can have a scenario in between. K is approximately 1. We're talking in the realm of, let's say, 0.01 to 100. Actually, yeah, that's correct. Where the proportion of concentration of products and reactants are very close to one another. Okay. This is the one we're going to look at the most, where we have a low K value, although as we move out of chapter 17 in chapters 18 and 19, we will look at heavily product favored and heavily reactant favored scenarios. But for now, that's what we're dealing with. Okay, and that will conclude this video, this introduction to equilibrium and equilibrium constants.